you have a question? Here.
For the last homework, the 5.2 said use a isosceles triangle, and everyone I talked to used an equilateral triangle, and that's the only way they knew how to.
Is an isosceles.
Which is a very special case of an isosceles triangle, but
So which is it, 5.2?
yeah.
Yeah.
And then in the book you say use isosceles, and I don't know anyone who figured it out how to use isosceles.
It's like a general
Oh,
isosceles.
really? I just said it had maximum length, a side length of epsilon.
Oh, you figured it out with.
I think,
Okay.
but that's what I did, is I just said, assume this is the maximum length.
Yeah.
And here's the maximum distance this can possibly be away.
Oh, you so you
Is how I did it.
So you put inequalities, maybe that's.
Yeah, but
Yeah. Do you? Yeah.
Well, for an isosceles.
All right, let's say that I'll let Keith Sanders resolve.
He said he wasn't going to grade
He
it.
says he was on time. We asked him.
That was his resolution.
Okay.
His resolution is avoid
Um,
conflicts.
Well,
Because it.
let me just read the thing. So you're saying it's much easier if you do an equilateral.
Yeah.
Uh-huh.
Also fine if you have a right angle triangle.
Also fun.
All right, look, I haven't done the problem in a long time, so I don't remember. If you want, I'll chat with you about it after class. Okay, the next topic is conformal mapping, and it's really very simple, so let me try to make it simple. So we've got some point here, Z, and I suppose maybe colored chalk would help. Boxes aren't the best place to color chalk. Okay, suppose we have a small displacement like that, and another one like that. And suppose in both cases, let's say that the dz is then epsilon e to the I theta, and dz prime is epsilon e to the I theta prime. And so we're talking then about angles. So this angle is theta prime, and this angle is theta. Okay? All right. Now, the point is that we can think about the angle between those two little vectors. And the angle between them is, I guess, if I'm going to continue with this colored chalk routine, it's dz prime over dz, so this is epsilon e to the I theta prime. And then I can see that this is why people don't use colored chalk across. Epsilon e to the I theta, and altogether, then this is equal to e to the I theta prime minus theta. So this is the angle then, theta prime minus theta, between these two small vectors in the complex plane. And now the whole point is that a function f of z takes each of these tiny vectors into something else. It maps them into other tiny vectors. And in particular, it maps them, and I guess I'll keep the color thing going, it maps them into dw, which is f of z plus dz minus f of z. And this is approximately, I'm assuming that f is analytic, of and analytic. Wherever we're going to be, it's analytic. So this is f prime of z dz. And on the other hand, dw prime is f of z plus dz prime minus f of z, and this is approximately f prime of z dz prime. Now the point is that dw prime over dw, well, what is it going to be? It's going to be f prime of z dz over, oh shit, I did the wrong color. And this is the dz prime, importantly. The prime here means first derivative. The prime here means other. Okay, so this is equal to dz prime over dz, and we already knew what that was. That is e to the I theta prime minus theta. So in other words, this analytic function maps dz into some dw, which might point that way. And if it does, then dw prime lags behind by the same angle. Okay? So in other words, angles are preserved by complex maps. So that's the whole point of this. Now, there is a simple subtlety here. Namely, this all relied upon my use of f prime of z. In other words, the way I got the answer that this angle is the same as that angle was to use f prime of z. Well, what happens if the function's analytic, but in some points the derivative vanishes? Well, now I'm going to switch back to ordinary chalk, so I don't have to curse anymore. So if we repeat the calculation, but now for the case in which if f prime of z equals 0, then dw prime over dw is going to be f double prime of z times a half dz prime squared, and we're dividing by fw prime of z a half dz squared, and so altogether then this is dz prime squared over dz squared, and this will be e to the 2I theta prime minus theta. So angles are doubled if the first derivative vanishes, but the second derivative is non-zero. And moreover, if f of z is equal to simply the nth, in other words, if all of the derivatives vanish except well, here's what I meant to say. In other words, if f of z plus dz minus f of z is 1 over n factorial, the nth derivative is e to the n, then dw prime over dw is going to be e to the I n theta prime minus theta. So angles get multiplied by a factor of n in that case. Okay, so an example is f of z equal to just c, z to the n. Now, at z equals 0, all the derivatives vanish, and the first up to the n. And so f of k of 0 is c n factorial delta nk. So if you don't differentiate enough, you just have z's left over and you get 0. You differentiate too much, you get 0 automatically. You differentiate just enough, just n times, you get this. And consequently, d phi prime over d phi is n d theta prime over d theta. Well, why did I write it that way? Anyway, the angles here. Phi prime minus phi is just simply n theta prime. So the angles go up by a factor. Okay, so that's the conformal business. Conformal, one of the features, an analytic map is said to be conformal, and what is meant by conformal is that the angles are preserved. So in other words, in particular, if you had a bunch of curves in the z-plane that were intersecting in various ways, and then you did a conformal map, you would then get, you could get something very strange, but whatever this mapped into, it would look like that, and whatever that mapped into, it would look like that, and whatever this mapped into, it would look somewhat like that. But where these actually are, you know, who knows? And I'm assuming that that all the first derivative non-zero. Yeah.
So the space that is in between the three curves, it can be the case that that space would not again be bounded by those three spaces?
I don't know. And the fact is that, I mean, you're quite right that this thing here is a closed curve, and it's got to map into a closed curve. I was just trying to be as elaborate as possible with the thing. You know, you could still probably make that into a closed curve. But a good point. I'm getting down very low on, I have to go to Costco tomorrow. Maybe late tonight. Any other questions? The next topic is Cauchy's principal value. And this is something that is used a great deal in physics courses, and so you need to understand it. And in fact, it once again is simple. And I think a lot of treatments of it in books that I've seen are sort of hasty or impatient or something, and can be confusing. So I tried to make this really clear. So in the interest of saving board space, let me start over here. I'm going to set k equal to some limit, epsilon going to 0, some integral from minus a to b of f of x over x minus I epsilon dx. So this is a particular integral that shows up, as I said, in physics courses. And so the first thing is we make use of something that we can attribute to Cauchy. Namely, that we first say this is the limit delta goes to 0 of, and now we go back to limit epsilon going to 0. And now we have 3 integrals instead of just 1. So we go from minus a to minus delta. And then we go from minus delta to delta. And then we go from delta to b. And close all the parentheses. Now, let me say that we're assuming that f of x is either differentiable or analytic, and so we can say it's approximately f of 0 plus x f prime of 0, plus higher order term, near x equals 0. Okay. The first thing is to use this Cauchy trick. We take this term and combine it with that term, and we call this the principal part. So the principal part of the integral from minus a to b of f of x over x dx is simply defined as, well, first of all, notice that inasmuch as we've separated out delta here, where delta is a finite positive number, we can let epsilon go to 0 here, and it's not going to make any difference in the first and the last integrals. So we can forget epsilon now. So we just have the limit delta going to 0 of integral minus a to minus delta f of x over x dx plus integral delta to b f of x over x dx. Okay, so this is what is called the principal part of the integral. So, in other words, it's not necessarily equal to the integral, but it's the principal part of the integral. And so, when you look at this, what you can see here is, suppose f of x is even at x equals 0, an even function. Well, then you're going to get contributions which could be very big from this integral, but they're going to cancel the contributions over here near x equals 0. So the singular part, the worst part of this integral, will cancel the worst part of this integral if f of x is even. And on the other hand, if it's odd, well then you've got a bit of a problem. And there's not much you can do about it. But if it's even, you can do something about it. And the reason why it very often is even is that if f of x is differentiable at x equals 0, then it's equal to f of 0 plus x f prime of 0, you see. So the f of 0 part is going to cancel. And the x prime, f prime of 0 part gives a finite number, a finite principal part. And in fact, okay, so that's that. So let me go on now. And so this principal part, by the way, is more general, namely the principal part of the integral from minus a to b of f of x over x minus y dx. Well, this is again limit delta going to 0 of an integral minus a to minus delta f of x, y minus delta, sorry, I have to read this thing, x minus y dx plus the integral from y plus delta to be f of x over x minus y dx. Okay, so the principal part of a more general integral of y, it's just defined in the same way, except that you just shift from 0 to 1. So that's the principal part. So now we can say that this k is equal to the principal part of this integral from minus a to b of f of x over x dx plus limit delta going to 0, limit epsilon going to 0, integral from minus delta to delta, f of x over x minus I epsilon dx. Okay, now what we can do is we can say that, so let me focus on the second term. So first of all, the limit delta going to 0, then the limit epsilon going to 0 of just minus delta to delta f of x over x minus I epsilon dx. Well, what can we say? Well, now, since we're near x equals 0, and we're saying that f itself is either analytic or at least differentiable, we can do this expansion here. And so we say, well, this is the limit delta going to 0, limit epsilon going to 0, integral minus delta to delta, and now up here we have f of 0 plus x f prime of 0 over x minus I epsilon dx. Okay, so it's hard to write down there, so let me turn the thing up here. So let me just say equals. In fact, maybe I should say equals up to here. The first one is the f of 0 term. So this we can factor out the f of 0, and we get f of 0 limit delta goes to 0, limit epsilon going to 0, integral minus delta delta, just dx over x minus I epsilon. And then we factor out the f prime of 0, and we have limit delta goes to 0, limit epsilon goes to 0, minus delta delta, x dx over x minus I epsilon. Okay, now this second term, this is pretty simple because we can just take this term and we can just take the limit epsilon going to 0. Well, when you do that, you just have the limit of x over x dx. That's the integral of 1, and that just gives you 2 delta. And we then have the limit of 2 delta as delta goes to 0, so maybe I'll keep this as 2 lines. So this is equal to f of 0, limit delta goes to 0, limit epsilon goes to 0, integral minus delta delta, dx over x minus I epsilon plus the prime of 0, lim delta goes to 0, 2 delta. Well, that's obviously going to be 0. And, okay, so now we focus on this one. And of course, what's going on here? Well, we can consider x to be a complex variable, and it's certainly, this thing 1 over, in other words, we can think of it as 1 over z minus I epsilon, and we're integrating from minus delta to delta, and originally we're going straight across. And we have a pole, but the pole is up here at I epsilon. It's in the upper half plane. So we can deform this as we like. We could make a small change, or we could just make it simple for ourselves and just make this a semicircle. And so we decide that we're going to rewrite this as f of 0 lim delta goes to 0, and epsilon goes to 0. And now this integral is going to be, let me do it explicitly here. It's will be an integral. I'll set z equal to delta e to the I theta, and I'll let theta go from pi to 2 pi. So this point is theta equal to pi, that's theta equal to 2 pi, and of course dz is I delta e to the I theta d theta, and so this is then the integral from pi to 2 pi I delta e to the I theta d theta. So that's the dz part, and then we're dividing by delta e to the I theta, and we can just let epsilon go to 0, well, minus I epsilon if you want, but now we can just let epsilon go to 0. Because in fact that's the instruction, let epsilon go to 0. Well then, this thing is just f of 0 times an integral pi I, this term, these terms all cancel. That we let go to 0, so we just have I pi times f of 0, of course. So now we've got a final evaluation of this thing. And the evaluation is that the limit epsilon goes to 0 of some integral minus a to b of f of x over x minus I epsilon dx is principal part of the integral from minus a to b of f of x over x dx plus I pi f of 0. Now, of course, we're assuming if f of x is approximately f of 0 plus x f prime of 0. In other words, we're assuming analyticity of f or differentiability of f. Okay? All right, so that's the rule. And in physics departments, we normally write this thing as 1 over x minus I epsilon is principal part of 1 over x plus I pi delta of x. Because if you substitute substitute for this principal part of 1 over x plus I pi delta of x, this term gives you that, and this term gives you I pi integral f of x delta of x dx, that gives you f of 0. And this thing has a, suppose we had the pole in the lower half plane. Well, in that case, we would be going, we'd have had something like an integral. We'd have, again, delta e to the I theta plus I epsilon. We'd have d theta. We'd have I delta e to the I theta. And we'd be integrating, well, what we'd have to do is we'd have to integrate from pi to 0 because we want to do this, don't we? In other words, the original line is this. The pole is here at minus I epsilon. That's a pole, not an x. So originally we were going to integrate across here. If instead we set z equal to e to the delta e to the I theta, then we go from pi to 0, and so this is minus I pi. And I forgot the f of 0 on this one. So the other relation is 1 over x plus I epsilon principal part 1 over x minus I pi delta of x. And more generally, obviously, the point x equals 0 is not special. It could have been y. And so we have x minus y plus or minus I epsilon is principal part of 1 over x minus y minus or plus I pi now delta x minus y. Okay, so that's basically the. So we've covered basically two tricks here. The first is Cauchy's definition of the principal part of an integral, which tells you how to handle a certain class of singularities when it's possible to handle them, and then how to handle things where you have an integral on the real axis plus or minus I epsilon. And so what we see is that it's the principal part minus or plus I pi delta of x minus y. Now, so I urge you to think about this and make sure you understand it, because it's something that we use in physics departments a lot. And in fact, instead of writing it that way, we normally just throw it out this way. Okay. So as an example, suppose we have the integral minus infinity plus infinity dx over x plus I epsilon times 1 plus x squared. Okay, I'm going to try to find the chalk that I was using that's fairly sharp. Well, this is the principal part of this integral. And then minus I pi, the integral delta of x over 1 plus x squared dx. And now this first one, this function is even, and so this principal part is just going to be 0. On the other hand, this one is going to give x equals 0, and so the answer is minus I pi.
That's odd, not even. If I take x to minus x, I get a minus sign.
Right, it's odd,
And that's why it's 0.
and consequently it's 0. Did I say even was good? All right,
Yeah.
well, it's, okay, we've got to distinguish. Can you switch the camera around, somebody? If f of x is even, where are we? If f of x is, where's the principal part? If f of x is even about x equal to a, the principal part is fine. F of x, here what I'm talking about, f of x over x. So let's swing this thing around. The analog of f of x, here f of x is 1 over 1 plus x squared. Okay. So there's some nomenclature thing. You just have to look at it and think.
The overall
It's just whether the bloody thing cancels or not. All right, let me toss you a candy for bringing out this difficulty with language here. All right, another example is, it turns out that just analytically, the integral dx over x squared minus a squared. This is an indefinite integral. This is minus 1 over 2a log, natural log, of course, x plus a over x minus a. You can verify that by just realizing that log of a ratio is the difference of the logs and differentiating each one, and you get that. And so there's an exercise to show that the principal part of this integral is actually 0. So principal part integral 0 to infinity dx over x squared minus a squared is 0. So the principal part of the thing is 0. All right, let's try now a different, another integral where we can use Cauchy's trick. Namely, this is an integral that also comes up in physics lecture, sine k over k dk. And so what do we do about this? Well, of course, we're going to set that equal to an integral e to the I k minus e to the minus I k over 2I k dk, 0 to infinity. And then, and the reason why we're doing that is that we're going to say that if we go to negative k, then this k absorbs a minus sign, and so this is the same thing as the integral minus infinity plus infinity, e to the I k over, I guess is it 2I k or just I k? Yeah, it's 2I k. Okay. So this is our integral, and what we're going to do is we're going to rewrite this as a principal part integral. In other words, we're going to say its limit, delta goes to 0 of the integral minus infinity to minus delta, e to the I k over 2I k dk, plus integral delta to infinity e to the I k 2I k dk. So that's the principal part. In fact, right, there's no I epsilon, so this just is the principal part. So this is the principal. So in other words, we're basically interpreting this as the principal part. E to the I k over 2I k dk. I hope that's not contagious. Oh boy. All right. I'll try to go through this really rapidly. So, so now we just use the Cauchy formula in reverse, and we say that I is equal to the principal part minus infinity plus infinity e to the I k over 2I k dk. So this is the integral from minus infinity to plus infinity e to the I k over 2I k plus I epsilon dk plus integral minus infinity plus infinity I pi delta of k e to the I k. And there I have 2I. What happened to k? Oh yeah, it's plus I pi delta of x. There is no k left. So in other words, remember here, it's 1 over x minus y, whatever, principal one, plus I pi delta. We don't keep the x minus y in the denominator. Okay, so we have these two things. Now, the first integral, what we do is we add a ghost contour in the upper half plane, because this pole is in the lower half plane. And because if we let k have a positive imaginary part, the thing is exponentially damped up in the upper half plane. So this is actually a ghost contour here. And so it's 0. So this whole thing is 0. On the other hand, this thing is pretty simple. It's just equal to I pi, period. Just I pi. And I'm sorry, there's a 2i here. I left out the 2i. So this goes away, but there's still 2i. And so it's I pi over 2i, which is pi over 2. Okay. So that means that the integral we started with, this integral is equal to pi over 2. So that's the result that we get. All right? Okay, let's see. It's getting, time is passing. I'm thinking of just mentioning, or I can jump back. If I see it, I can step over it. It's when I don't see it, I kick it by mistake. All right, the next topic is Feynman's propagator, and I think I'm going to, we can vote on this, okay? We don't need to go through it.
I want to see it, but it's really long.
It is long. Well, you can see it, it's in the book.
Yeah, I want to see it.
You want to see me? All right. Okay, let's have some voting then. This Feynman propagator is something that's important in quantum electrodynamics, quantum field theory, and so forth. On the other hand, I'm trying to stay far away from this. You're in the.
I'm not sick.
You're in the dead zone.
I'm not sick. I'm not sick. My pop is from smoking cigarettes. No smoking.
Yeah, let me just say something about smoking. When I was young, and even dumber than I am now, I smoked cigarettes for a while. And of course, in those days, everybody smoked cigarettes. Almost everybody. Anyway, let me make this really rapid. The most important thing you can do is to stop smoking cigarettes. The carbon monoxide deprives your brain of oxygen, and so you don't learn as well. The nicotine screws up your circulatory system because it whacks the heart and so forth. And then among the things that kill you in the smoke are polonium-210, which is radioactive and a heavy metal, and therefore also toxic. So it's poisonous and it's radioactive. And you breathe it in, it just attaches somewhere to your lung cells. And, if you get polonium on your skin, it's no big deal. If you get polonium on your lung, it's a big deal. And the reason is that your skin is constantly producing first of all, the outer layer of the skin is dead cells, and your skin is constantly producing new cells, and the new ones bud, and they push the young ones up, and they push the middle ones up, and they push the old ones up to the top where they die and slough off. So it's no big deal. The lung is different. And the other thing that's in the tobacco smoke is lead-210, which is a radioactive isotope of lead. Lead, of course, is also toxic, and lead-210 is radioactive. Polonium-210 is what the Russians used to kill somebody or other, I forget who it was in England, and I don't know, they poured some polonium-210 in his tea when he wasn't looking, and he was dead as a doornail in 6 months or something. I don't know how long it was, but yeah. So if you're coughing like that because of smoking, then you really, really need to stop. Yeah. Well, it's hard, but it's not hard forever. It's really hard for 2 weeks. And then after 2 weeks, it's not really hard, it's just hard. And then it's maybe just hard for another 2 weeks. And once you got past a month, it's no longer even hard. But there is one problem, namely that if you stop smoking for a month and you smoke one cigarette, it's like you've gone to heaven. So you've got all these receptors on these neurons in your brain that are just go bananas when they get that nicotine. So you've got to get through, you've got to resist the temptation to smoke after you no longer need to smoke. And then after about 6 months or a year, you'll start to hate smoke, cigarette smoke, as much as I do. All right, so that's the commercial. Okay, let's have a vote here.
You know, you could always just go and work for Bernie Sanders.
Well, I bought his, I'm afraid Bernie doesn't have enough money, but I hope he's got a zillion small contributions. I'll take over. Bernie Sanders t-shirt. Huh?
I like the idea.
All right, let's have a vote. How many people want me to actually go through the Feynman propagator rather than just say a couple of words about it?
Do we have time?
Okay, so I have one. All right, we seem to have 6, 4. And how many don't want to see it? I guess the others, so. All right, raise your hand if you don't want to see it, because we've got to count this thing. Oh, Christ. I was certain you didn't want to see it, so I didn't prepare this part. But of course I can, do it anyway. So, all right, let me try to go through this thing. As I said, I hadn't really thought. First of all, what's the differential equation? Well, it's m squared minus box on some Green's function, which is normally written as big triangle delta f, and we want that to be a 4-dimensional delta function. So here x is x0, x1, x2, x3. I'm using superscripts instead of subscripts because the convention is that you flip the sign of the coordinates, either the space coordinates or the time coordinates, when you lower the superscript to a subscript. And if I keep them up, I don't need to change any
So is that
signs.
covariance versus contravariance?
Yeah, sort of, but because this is special relativity, the difference isn't that big. And in fact, Feynman's attitude was, just put in a minus sign where it goes, and you know where it goes. And that's Feynman always was right. This thing with box is equal to triangle minus d2 dt squared, and equivalently, this is triangle minus d2 dx0 squared. Here, x0 really is supposed to be ct, but I'm going to set c equal to 1 to make the equation simple here. If you put in c and h bar, then everything gets complicated. It just gets really sort of messy. So we're using what I call natural units, where h bar and c are 1. Okay, I guess that's that. I once heard a very good lecture by a string theorist who said, at the very beginning, he said, I'm going to be using units where h bar and c and 2 and I and minus 1 are equal to 1. And that's because he wanted just to give us the qualitative picture of what he was doing. Of course, everybody laughed when he said that. Okay, delta fourth of x, of course, is just this thing that we learned when we were doing Fourier transforms, but we can do it, we can say it's this, we can say it's q dot x minus q0 x0. Of course, you could equally well have plus q0 x0, because and you could also have a minus sign here. So it's this form itself automatically gives you delta fourth of that. So then the question is, what do you need for this equation to be true? And clearly what you need is for delta F, F stands for Feynman, of course, is integral. By the way, he wrote a lot of books, and they're all marvelous. Some of them are for the general public, and some of them are, I'm laughing because they're said to be for freshman physics classes, but what they really are is for smart PhDs. The problem with Feynman's lecture style is that he was so smart that he could reinvent the physics that was appropriate for each problem. So that meant the solution was very rapid. The trouble was the theory was different for each problem. And so the student then has to jump from page to page. It's you do physics this way, and then, well, you know, you have all these different ways of looking at physics, and so you now have a new theory, and this new theory is exactly suited to problem 2, and then you have another theory that's exactly suited to problem 3. So that's basically the problem with Feynman's books. But he wrote, but of course, you know, with a little struggling, you know, they're still marvelous books to read, and I encourage that you suffer through them. Okay, the point is that this is a proper Green's function for this differential operator, because when this differential operator hits all these derivatives, and they're double derivatives with respect to x0, x1, x2, x3, they just bring down q0 squared with a minus q0 squared with 2 i's. So they bring down iq0 squared, or iq1 squared, or iq2 squared, or iq3 squared, and so forth. And they do it in such a way as to give us q squared, and this particular q squared is q0 squared minus q vector squared. And the reason why they come that way is that in this q dot x, we've got an extra minus sign here. So when you differentiate with respect to the time variable, yes, when you differentiate with respect to the, I wrote that wrong. That's the other metric. This minus sign gives you the extra minus sign on the q0 squared. So, and then the m squared comes along. So when you have m squared minus box acting on delta f of x, what you get is d4th q over 2 pi to the 4th. And then, of course, you get m squared, but then you get minus, and then, well, the minus sign is canceled because you have 2 i's all the time, I squared. And then the d by dx squared gives us a q squared, and then you have minus q0 squared, and that's divided by m squared plus q squared, where this is exactly the same as that. And then the exponential remains as e to the I q dot x. And so this cancels, that's just 1, and then this is just delta 4th of x. And I left out this minus I epsilon there. And so what I'm saying is that apart from the minus I epsilon, this is obviously a solution. In other words, you take the only time you have to be careful about the minus I epsilon is when q squared is equal to minus m squared. So you need to pay attention there. But apart from that, you're getting delta of x. So this thing is delta of x apart from this this issue with the minus. In fact, there isn't even any issue with the minus sign. I misspoke there a moment ago. It's because this is basically something over something minus I epsilon. And if this denominator is 0, so is the numerator. So you can take the limit at epsilon going to 0. So we have this thing exactly, no matter what epsilon is, you just take the limit epsilon goes to 0. Okay, so that's that part of it. Now the question is, what is this minus I epsilon doing? Well, let me skip to the end. If we skip to the end, what we'll find out is that minus I times the Feynman, what is it? Feynman something. The Feynman propagator is the mean value in the vacuum of the time-ordered product of two scalar fields of mass m. Not of mass m, but describing three particles of mass m. And so the I epsilon is giving you the time ordering. That's what the I epsilon is doing. Okay. Now, that's the main thing. The rest of it is an example of complex integration together with a lot of detail. You guys want to see that, or should I skip that? All right, you decide. I'm having trouble getting an election. Huh?
I'd say we can skip it and keep going, but I am curious as, so you said it's useful for quantum field theory and a couple of other things.
Quantum electrodynamics.
And, okay, how exactly, or where does it show up?
Okay, well, all right. Well, you guys have heard about Feynman diagrams, right? And in particular, if we imagine describing nucleons as exchanging pions, that's one way of describing low energy neutron-proton type interactions. Then what you might have is you might have a proton do this, and then you draw something like that. And this Feynman diagram means you have a proton going along with, say, P1 to P2, and this one K1 to K2. So these are the four momenta of, the momenta of the ingoing and outgoing protons. This would be a pi 0, which has a mass of around 140 MeV. C squared if we keep that. Keep that in mind. And so this is, we say this is a virtual particle. It's exchange. And what does that mean? Well, in the actual calculation, this part of the thing is just a number that, well, everything is just a number when you're doing a calculation. But this thing is a simple number that together with some phase factors. These two are a simple number together with some phase factors. And this thing here is going to be 1 over, let us say, P2 minus P1 squared. It's going to be exactly this propagator, plus m squared. And here the minus I epsilon doesn't matter. In diagrams like this, you could forget about the minus I epsilon. So in other words, this propagator gives you the amplitude in momentum space with this calculation. And then there's a constant up here. And these are the four momenta here. So literally this is P2 minus P1 3 vectors squared minus E2 minus E1 squared plus m squared. And what this tells you is that this force is basically short range. It has a range, instead of being a Coulomb potential, it's e to the minus r times mu over 4 pi r, essentially. So that's basically, in other words, if you are thinking about this so that it's space rather than time, you ignore the time part, this is the propagator, or this is the potential. Whereas in if the mass, you take the mass mu going to 0, this just becomes 1, and that's a Coulomb force. And there's also a certain subtlety here that I might as well mention since it's a physical subtlety. Suppose you quantize electrodynamics in the Coulomb gauge. The Coulomb gauge is that you say the vector potential has no divergence. And this is the most physical gauge because then you get just transverse photons, which is the way we normally think about photons. Well then, it turns out your propagator is just the same as this, except m is 0. And of course you keep the I epsilon in general because it's in complicated diagrams it's important. Now what does this represent? This represents not only the exchange of the real photons, but also the Coulomb field. And so one can say that for electron scattering, say, this diagram represents not only the actual exchange of a real photon or a virtual photon, but also the fact that this electron has negative charge, it generates a Coulomb field, and this other one is scattered by it. And that's why, for example, when biologists talk about, what the hell's the name? I forget. The name is that if you excite a certain fluorophore, a nearby fluorophore, if it's close enough, it can be excited by electrostatic effects, and then it can de-excite, and it can give off a photon of a different color. And so if you have things set up the right way, you might excite a, say, a blue fluorophore, and then if the red fluorophore is far away, all you get is you excite the blue, and then it sends out, it de-excites, and gives you a blue photon. If the red one is close, then you get you often get a red photon coming out. And the proper description about what's going on is that you have effectively an electrostatic effect, but you can describe the whole thing with the Feynman propagator because that includes the electrostatic as well as the actual transfer of the photon. Okay, long story there. All right, let's okay, I don't know. I think maybe I'll just skip the rest of this, shall I? Because I'm not going to be able to get through it in 5 minutes. So let me start then dispersion relations, and I can at least give you the main idea of dispersion relations. The first idea is that suppose you have an effect at time t, which is due to some cause at time t prime, dt prime, and then there's some transfer, f hat, of t minus t prime, and we just say in general it's this integral. Okay? On the other hand, we don't believe in magic, and so we say that this transfer function has to be 0. That is to say that the cause has to be before the time. Okay, so f hat of t minus t prime is is not equal to 0 only when t minus t prime is greater than 0. So in other words, we could rewrite this as an integral from minus infinity to t of f hat of t minus t prime, c of t prime dt prime. So in other words, only the causes before the effect matter, and that's guaranteed because if we did the whole integral, f would vanish for arguments, for negative arguments, basically. It's that f hat of t minus t prime is 0 for t minus t prime less than 0, so for negative times. And that means then if we consider the Fourier transform of f hat, the transfer function, e to the I z t dt, and we can put a square root 2 pi, I don't know why I did that. But then what do we have? Well, this integral actually is only over positive values because the transfer function vanishes for negative values of time. And so this is actually just the integral 0 to infinity e to the I z t f hat of t dt over again root 2 pi. And now what does this tell us? This tells us that since t is always positive, z, this e to the I z is damped when z has a positive imaginary part. So then you have e to the I t x plus I y. So if y is positive, you have minus ty. So this is e to the minus ty e to the I x t. This damping, e to the minus ty, means that this function here is analytic in upper half plane. Well, again, as long as f hat is not, I say here an arbitrary transform, it's not, as long as it's not some hyperpathological thing dreamt up by somebody in a math department. All right. So now, what we normally do is say, well, this f is analytic in the upper half plane. Let's make one more assumption that makes things useful. Let's just write it as r e to the I theta. And what we want to say is that the limit of this is 0 as r goes to infinity. And in fact, we're really only concerned with that is if theta is, that's a pi. Theta is between 0 and pi, so that r e to the I theta is in the upper half plane, or maybe on the real axis, and it goes to 0 as r goes to infinity. In that case, then, here, let me write one more equation, and then we can write f of z0 just by using Cauchy's formula. We have analyticity then in the upper half plane, and we can write this as an integral f of z over z minus z0 dz, where z0 is some point in the upper half plane, and we go, say, along the real axis, and then like this. Well, it turns out that because I assumed that f goes to 0 in the upper half plane as you go, way out, this part is a ghost contour, and so this is just 1 over 2 pi I integral f of x dx over x minus z0. And now we let the imaginary part, we said let me see if I have this notation exactly right. I'm going to let Z0 go to X0 X0 plus I epsilon, and then this thing becomes 1 over 2 pi I integral minus infinity plus infinity f of x dx over x minus x0 minus I epsilon. So now you see why I emphasize the Cauchy trick and the 1 over I epsilon rule. Namely, that this is 1 over 2 pi I, principal part of this integral, minus infinity plus infinity, f of x over x minus x0 dx, and then plus I pi integral f of x delta x minus x0 dx. And so what we get is that this is principal part over 2 pi I f of x over x minus x0 dx plus I pi f of x0. And on the other hand, what were we computing? Well, we were computing f of z0, but z0 is x0 apart from epsilon. So we get f of x0 equals 1 over 2 pi I, this integral, plus I pi, like that. And I screwed something up. We had a 2 pi I in the denominator. So this is actually f of x0 over 2. So then our equation is f of x0 is principal part over pi I of the integral. F of x over x minus x0 dx. Okay, so this is the generic dispersion relation. And I'll pick this up next time. You can then play with this in various ways. So the thing basically is you have analyticity in the upper half plane, and then you assume that the function goes to 0 fast enough, and so that this is a ghost contour. Then you use the Cauchy and the 1 over f pi epsilon trick, and bingo, you're done. Okay, I guess we can quit now.